For most of human history, the night sky seemed calm, predictable, and familiar. The stars appeared fixed in place, forming patterns that ancient civilizations turned into myths and constellations. To early observers, the cosmos felt ordered, almost permanent, a grand celestial ceiling stretching endlessly above the earth. But that sense of certainty was an illusion. As centuries passed and human curiosity deepened, the tools of observation improved. Telescopes revealed that the stars were not fixed points at all, but distant suns scattered across unimaginable distances. Entire galaxies, vast islands of stars, emerged from the darkness, each containing billions of worlds. The universe, once thought to be small and static, was suddenly revealed to be dynamic and immense. In the 20th century, discoveries accelerated at a breathtaking pace. Scientists uncovered evidence that the universe is expanding, that galaxies are racing away from each other, and that everything we see today originated from a single, violent beginning known as the Big Bang. This revelation transformed our understanding of reality itself. Yet even as our knowledge grew, so did the mysteries. Invisible forces like dark matter and dark energy emerged to explain observations that defied logic. Entire regions of the cosmos remained hidden beyond our reach, and fundamental questions about the origin, structure, and fate of the universe remained unanswered. Then, in the 21st century, humanity built something extraordinary. High above Earth, far beyond the orbit of the Moon, a powerful observatory began unfolding itself in the darkness of space. This instrument was designed to do something no telescope had ever done before, to look deeper into the past than ever imagined. That instrument is the James Webb Space Telescope. Unlike its predecessors, Webb does not primarily observe visible light. Instead, it captures faint infrared signals, ancient light stretched across billions of years by the expansion of space itself. This allows it to peer into an era when the very first galaxies were forming. It is, in every sense, a time machine, and what it has revealed is deeply unsettling. Galaxies that appear far too massive for their age. Structures that formed far earlier than our theories predicted. Patterns that challenge the very foundation of modern cosmology. Some scientists, including Nobel Prize-winning astrophysicist Adam Rees, have begun to suggest that something is not quite right. That perhaps we are missing something fundamental. To understand these discoveries and why they matter, we must first explore the incredible technology that made them possible. For more than 3 decades, one telescope defined humanity's view of the universe. The Hubble Space Telescope. Launched in 1990, Hubble transformed astronomy. Its images revealed glowing nebulae where stars are born, galaxies colliding in slow-motion cosmic dances, and deep fields filled with thousands of galaxies in regions of space once thought empty. Hubble helped scientists measure the expansion rate of the universe and refine its age to approximately 13.8 billion years. It became one of the most important scientific instruments ever created. But even Hubble had limits. The earliest galaxies in the universe are incredibly distant. Their light has traveled for more than 13 billion years to reach us. During that time, the expansion of the universe has stretched this light, shifting it out of the visible spectrum and into infrared wavelengths. Hubble, designed primarily for visible light, could only see part of this ancient signal. To go further, to truly observe the birth of galaxies, scientists needed something entirely new. The solution was ambitious beyond precedent. For more than 3 decades, one telescope defined humanity's view of the universe. The Hubble Space Telescope. Launched in 1990, Hubble transformed astronomy. Its images revealed glowing nebulae where stars are born, galaxies colliding in slow-motion cosmic dances, and deep fields filled with thousands of galaxies in regions of space once thought empty. Hubble helped scientists measure the expansion rate of the universe and refine its age to approximately 13.8 billion years. It became one of the most important scientific instruments ever created. But even Hubble had limits. The earliest galaxies in the universe are incredibly distant. Their light has traveled for more than 13 billion years to reach us. During that time, the expansion of the universe has stretched this light, shifting it out of the visible spectrum and into infrared wavelengths. Hubble, designed primarily for visible light, could only see part of this ancient signal. To go further, to truly observe the birth of galaxies, scientists needed something entirely new. The solution was ambitious beyond precedent. The James Webb Space Telescope was conceived as the most powerful space observatory ever built. Its design pushed the boundaries of engineering, physics, and human ingenuity. At its heart lies a massive primary mirror composed of 18 hexagonal segments, each coated in a thin layer of gold. When fully deployed, this mirror spans 6.5 meters, more than twice the diameter of Hubble's mirror, giving Webb an unprecedented ability to collect faint light from distant objects. But Webb's true power lies in its sensitivity to infrared radiation. To detect such faint signals, the telescope must operate at extremely low temperatures. Even the slightest heat from the sun, Earth, or moon could overwhelm its instruments. From this distant vantage point, Webb began its mission: to see the first light in the universe. When we look into space, we are not just observing distant objects. We are looking back in time. Light travels at an astonishing speed, about 300,000 kilometers per second. Yet even at this speed, the vast distances of the universe introduce delays that reshape our perception of reality. The light we see from the moon is already 1.3 seconds old. The sun, as we perceive it, exists 8 minutes in the past. But when we observe distant galaxies, the effect becomes extraordinary. Some of the galaxies detected by the James Webb Space Telescope are so far away that their light has taken more than 13 billion years to reach us. This means we are seeing them not as they are today, but as they were when the universe itself was still in its infancy. This concept, known as look-back time, transforms telescopes into time machines. By observing increasingly distant objects, astronomers can reconstruct the history of the universe, step by step, tracing its evolution from the present day all the way back to its earliest moments. Shortly after the Big Bang, the universe was a hot, dense, and rapidly expanding environment. Over time, it cooled, allowing the first atoms to form. Eventually, gravity began pulling matter together, creating the first stars and galaxies. For decades, scientists believed they had a reasonably accurate picture of how this process unfolded. But when Webb began observing the early universe, something unexpected emerged. The timeline didn't quite match. The galaxies Webb was detecting appeared far more developed than they should have been. Instead of small, primitive systems just beginning to form, many of these galaxies already looked mature, massive, bright, and structured. It was as if the universe had skipped steps, or evolved faster than we ever thought possible. According to traditional models of cosmic evolution, the formation of galaxies was a gradual process. After the Big Bang, the universe entered a period often referred to as the cosmic dark ages. During this time, there were no stars, no galaxies, only vast clouds of hydrogen and helium gas slowly drifting through space. Over hundreds of millions of years, gravity began to pull this matter together. Regions of slightly higher density attracted more material, growing larger over time. Eventually, these dense pockets collapsed under their own gravity, igniting the first stars. These early stars were unlike anything we see today. They were massive, short-lived, and composed almost entirely of primordial elements. As more stars formed, they grouped together into small galaxies, simple, irregular structures that would later merge and evolve into the complex galaxies we see today. At least that was the theory. But observations from the James Webb Space Telescope suggest a very different story. Instead of small, slowly growing galaxies, Webb has identified objects that appear surprisingly large and mature, even at extremely early times in cosmic history. Some of these galaxies seem to contain billions of stars, and they existed when the universe was less than 1 billion years old. This raises a profound question. How did they grow so quickly? When the first deep-field images from the James Webb Space Telescope were released, astronomers around the world reacted with excitement. But that excitement quickly turned into confusion, and then concern. Buried within Webb's observations were galaxies that simply should not exist, at least not according to our current understanding of the universe. These galaxies were not faint, barely forming structures. They were bright, massive, and surprisingly well organized. Some appeared to rival the size of galaxies that, according to theory, should have taken billions of years to form. Yet here they were, already in place, already evolved, at a time when the universe was still in its infancy. Scientists began referring to them informally as impossible galaxies. Because under the standard cosmological model, the lambda-CDM model, there simply wasn't enough time for such structures to emerge. In this model, galaxies grow gradually through a process known as hierarchical formation. Small structures merge to form larger ones over immense spans of time. But Webb's observations suggest something very different. Instead of slow growth, the early universe may have experienced a period of rapid, almost explosive galaxy formation. Stars forming at extreme rates, matter collapsing faster than expected, structures assembling with surprising efficiency. One possible explanation is that early star formation was far more intense than previously believed. In these early galaxies, gas may have been converted into stars at astonishing speeds, producing massive systems in a fraction of the expected time. Another possibility is more unsettling. What if our models are incomplete? What if key pieces of the cosmic puzzle are still missing? Some researchers have even suggested that entirely new physics may be required to explain what Webb is seeing. And if that is true, then the universe we thought we understood may be only part of a much larger story. On the largest scales, the universe reveals a pattern that is both beautiful and astonishing. Galaxies are not scattered randomly across space. Instead, they form an immense interconnected structure known as the cosmic web. This vast network stretches across billions of light-years. It is composed of long filaments filled with galaxies and galaxy clusters, intersecting at dense nodes, while enormous empty regions, called voids, separate them. If we could zoom out far enough, the universe would resemble a three-dimensional web or sponge, with matter concentrated along thin strands and vast emptiness in between. This structure did not form by chance. It is the result of gravity acting over billions of years, amplifying tiny fluctuations in the density of matter that existed shortly after the Big Bang. But gravity alone cannot explain the speed and scale of this formation. To understand the cosmic web, we must consider something we cannot see, something that does not emit light, something that makes up most of the matter in the universe. The visible universe, the stars, planets, and galaxies we can observe, represents only a small fraction of what actually exists. Most of the universe is invisible. This unseen component is known as dark matter. Unlike ordinary matter, dark matter does not interact with light. It does not shine, reflect, or absorb radiation, cannot be observed directly with telescopes. And yet, its presence is undeniable. Astronomers first discovered evidence for dark matter by studying the rotation of galaxies. Stars at the outer edges of galaxies were moving far faster than expected. According to the laws of physics, they should have been flung into space. But they weren't. Something invisible was holding them together. That something was dark matter. Today, scientists estimate that dark matter makes up about 27% of the universe. It forms massive halos around galaxies, providing the gravitational framework that allows them to exist. Even more importantly, dark matter played a crucial role in shaping the cosmic web. In the early universe, regions rich in dark matter acted as gravitational anchors, pulling in ordinary matter and accelerating the formation of galaxies. Without dark matter, the universe as we know it would not exist. But despite decades of research, we still don't know what dark matter actually is. And now, Webb's discoveries are raising new questions about how it behaves. Could dark matter have interacted differently in the early universe? Could it have accelerated galaxy formation in ways we don't yet understand? If so, the implications would be profound. If dark matter governs the structure of the universe, another force controls its destiny. That force is known as dark energy. For much of the 20th century, scientists assumed that the expansion of the universe, first discovered by Edwin Hubble, would gradually slow down over time due to gravity. After all, gravity pulls matter together. It seemed logical that it would eventually slow the outward motion of galaxies. But in 1998, Two independent teams of astronomers studying distant supernova explosions made a shocking discovery. The universe was not slowing down. It was speeding up. Galaxies were moving away from each other faster and faster. Something was pushing the universe apart. That something became known as dark energy. Today, scientists estimate that dark energy makes up nearly 68% of the universe, making it the dominant component of reality itself. And yet, like dark matter, its true nature remains unknown. Is it a property of space itself? Is it a new kind of energy field? Or does it point to a deeper flaw in our understanding of gravity? The answers remain elusive, but Webb's observations may provide new clues. By studying distant galaxies and the expansion of the universe with unprecedented precision, the telescope could help scientists refine their measurements of cosmic expansion, and possibly reveal whether dark energy behaves differently over time. One of the most pressing mysteries in modern cosmology is known as the Hubble tension. It centers around a fundamental question: how fast is the universe expanding? This rate of expansion is described by a value known as the Hubble constant. But there's a problem. Different methods of measuring the Hubble constant produce different results. When scientists measure expansion using nearby galaxies, observed with telescopes like Hubble, they get one value. When they analyze the early universe using data from the cosmic microwave background, they get a different value. And the two don't agree. This discrepancy is not small. It is significant enough to suggest that something may be fundamentally wrong with our current models of the universe. Now, with the arrival of the James Webb Space Telescope, scientists hoped to resolve this tension. By providing more precise measurements of distant stars and galaxies, Webb could help refine the value of the Hubble constant. But instead of resolving the issue, it may be making it worse. Early results suggest that the discrepancy remains, and may even be more pronounced than before. If this tension cannot be resolved, it could point to new physics beyond the current cosmological model. Are we missing something fundamental? Science advances by building models, mathematical frameworks that describe how the universe behaves. For decades, the lambda-CDM model has served as the foundation of cosmology. It explains the large-scale structure of the universe, the formation of galaxies, and the distribution of matter across space. It has been remarkably successful. But no model is perfect, and when observations begin to conflict with predictions, scientists must ask a difficult question. Is the model incomplete, or is it fundamentally wrong? The discoveries made by the James Webb Space Telescope are beginning to push this question to the forefront of modern astronomy. If galaxies formed earlier and faster than expected, if the expansion rate of the universe cannot be consistently measured, if dark matter and dark energy behave in ways we don't yet understand, then it may be time to rethink our assumptions. Some researchers believe we may be on the edge of a scientific revolution, a moment similar to the shift from Newtonian physics to Einstein's theory of relativity, a moment when old ideas give way to deeper truths, and when the universe reveals itself to be far stranger than we ever imagined. The story is far from over. In fact, it is only just beginning. The James Webb Space Telescope has only been operational for a short time, and its discoveries are already reshaping our understanding of the cosmos. In the coming years, it will continue to observe distant galaxies, study the atmospheres of exoplanets, and probe the earliest moments of cosmic history. New telescopes, both on Earth and in space, will work alongside Webb, providing complementary data and expanding our observational capabilities. Together, these instruments will help scientists test new theories, refine existing models, and explore the unknown. Because that is the nature of science. It evolves, it adapts, corrects itself, and with every new discovery, it brings us closer to the truth. At first glance, these discoveries may seem distant, abstract questions about galaxies billions of light-years away, but they are deeply connected to us. Understanding the universe is, in many ways, understanding our own origins. Every atom in your body was forged in the carbon of ancient stars. Every element heavier than hydrogen was created through cosmic processes that began billions of years ago. We are, quite literally, made of stardust. And by studying the universe, we are uncovering the story of how we came to exist. The deeper we look into space, the more the universe surprises us. What once seemed simple becomes complex. What once seemed understood becomes uncertain. And what once seemed impossible becomes reality. The discoveries of the James Webb Space Telescope have opened a new chapter in humanity's exploration of the cosmos. A chapter filled with mystery, with questions, and with the possibility that our understanding of the universe is only just beginning. Because in the end, the universe may not be what we thought it was. It may be something far more extraordinary. Something still waiting to be discovered. For decades, scientists believed they had mapped out a reliable timeline of the universe. It was a story built carefully, piece by piece, using observations, equations, and simulations. According to this timeline, the universe began with the Big Bang approximately 13.8 billion years ago. In the beginning, there were no stars, no galaxies, only a hot, dense plasma of particles and radiation. As the universe expanded and cooled, atoms formed. Then, after hundreds of millions of years, gravity ignited the first stars, marking the end of the cosmic dark ages. From there, galaxies slowly assembled. Small structures merged into larger ones. Order emerged from chaos. At least, that was the expectation. But the data from the James Webb Space Telescope is forcing scientists to reconsider this entire sequence. Galaxies are appearing earlier than predicted. Not just slightly earlier, but dramatically earlier. Some observations suggest that complex, massive galaxies may have existed just a few 100 million years after the Big Bang. If these measurements are correct, then the timeline we trusted may be incomplete. Or worse, fundamentally flawed. Because if galaxies formed earlier, it means the processes that created them must have operated faster or differently than we thought. This isn't just a small adjustment. It's a shift that could ripple across all of cosmology. The early universe was a race against time. After the Big Bang, matter began to spread out rapidly. As space expanded, densities dropped, making it harder for gravity to pull material together. In this environment, forming large galaxies should have been extremely difficult. There simply wasn't enough time. And yet, Webb is showing us galaxies that appear to have formed with incredible speed. To understand just how strange this is, imagine trying to build a massive city overnight, with no infrastructure, no materials, and no workforce. That's essentially what these early galaxies represent. They are cosmic structures that seem to have assembled far too quickly. So how could this happen? One possibility is that the early universe was far more efficient at forming stars than it is today. Gas clouds may have collapsed rapidly, triggering intense bursts of star formation known as starbursts. In these environments, stars could have formed at rates hundreds of times faster than in modern galaxies. But even this may not be enough to explain the largest structures Webb has observed. Which leads to a deeper possibility. What if something else accelerated the process? Throughout history, major scientific breakthroughs have often followed moments of confusion. When observations no longer match theory, it signals an opportunity. A chance to discover something new. The anomalies revealed by the James Webb Space Telescope may represent such a moment. Some scientists are beginning to explore the possibility that new physics may be required to explain what we are seeing. This could take many forms. Perhaps dark matter behaves differently than expected, interacting more strongly in the early universe. Perhaps there were additional forms of matter or energy present shortly after the Big Bang that no longer exist today. Or perhaps our understanding of gravity itself is incomplete. There are even theories suggesting that the laws of physics may have evolved over time, that the early universe operated under conditions very different from those we observe today. These ideas may sound radical, but so did many scientific truths when they were first proposed. The idea that Earth orbits the Sun was once controversial. The concept of an expanding universe was once doubted. And the existence of dark matter and dark energy remains one of the greatest mysteries in science. Now, Webb may be pointing us toward the next breakthrough. Another surprising discovery from Webb involves the presence of supermassive black holes in the early universe. These objects, millions or even billions of times more massive than the Sun, are typically found at the centers of galaxies. In the modern universe, they are thought to grow slowly over time, accumulating mass as they consume surrounding matter. But Webb has detected evidence of massive black holes that existed far earlier than expected. Some appear to have formed less than 1 billion years after the Big Bang. This raises a critical question. How did they grow so large so quickly? One possibility is that these black holes formed from the direct collapse of massive gas clouds, bypassing the usual stages of stellar evolution. Another possibility is that they experienced rapid growth through intense accretion, feeding on vast amounts of matter in the early universe. These early black holes may have played a key role in shaping galaxies. Their immense gravity could have influenced star formation, regulated the growth of galaxies, and contributed to the large structures Webb is now observing. In this sense, black holes may not just be cosmic endpoints. They may be architects of the universe itself. There was a time when the universe was completely dark. After the initial glow of the Big Bang faded, the cosmos entered a period known as the Dark Ages. During this time, there were no stars to illuminate space. Only vast clouds of neutral hydrogen filled the universe. Then something changed. The first stars ignited. These stars emitted intense radiation, gradually ionizing the surrounding gas and allowing light to travel freely through space. This period is known as the Epoch of Reionization, one of the most important transitions in cosmic history. The James Webb Space Telescope is uniquely suited to study this era. By observing extremely distant galaxies, it can detect light from this transformative period. And what it is finding suggests that reionization may have occurred earlier and more rapidly than expected. Once again, the timeline appears compressed. The universe was evolving faster than we thought. Could we be wrong about everything? Science is built on evidence, but it is also built on assumptions. Assumptions about how matter behaves, about how gravity works, about how the universe evolves. Most of the time, these assumptions hold, but sometimes new data forces us to question them. The discoveries made by the James Webb Space Telescope are doing exactly that. They are challenging long-held beliefs about the early universe. They are exposing gaps in our models. And they are raising a profound possibility. What if our understanding of the universe is incomplete? Not entirely wrong, but incomplete, missing key pieces of a much larger puzzle. This is not a failure of science. It is its greatest strength. Because every time we discover something unexpected, we move closer to the truth. The universe is not simple. It is layered, complex, dynamic. Every time we think we understand it, it reveals something new. The discoveries of Webb are not just adding details to an existing picture. They are changing the picture itself. Galaxies forming earlier, black holes growing faster, structures appearing more organized than expected. All of this points to a universe that is more efficient, more dynamic, and more mysterious than we ever imagined. And perhaps, more beautiful. Right now, humanity stands at a unique moment in history. For the first time, we have the tools to observe the earliest chapters of the universe with extraordinary precision. We are no longer guessing. We are seeing. And what we are seeing is rewriting our understanding of reality. The James Webb Space Telescope is not just a telescope. It is a gateway, a window into the past, a machine that allows us to explore the origins of everything. And with every new image, every new dataset, every new discovery, it brings us closer to answering the biggest questions ever asked. Everything we have ever observed, every galaxy, every star, every structure mapped by telescopes like the James Webb Space Telescope, exists within a limited region known as the observable universe. This boundary is not a physical wall. It is a limit set by time. Because light travels at a finite speed, there are regions of space so distant that their light has not yet had enough time to reach us. Beyond this horizon lies a vast expanse we cannot see, and may never see. And yet, there is no reason to believe the universe ends there. In fact, most cosmologists suspect that what we observe is only a tiny fraction of a much larger reality. Possibly infinite, possibly filled with structures far beyond anything we can imagine. The discoveries made by Webb, galaxies forming earlier, structures appearing more complex, raise an intriguing possibility. If the universe is already this rich and surprising within our observable region, what might exist beyond it? To understand the true scale of the universe, we must return to its earliest moments. Immediately after the Big Bang, the universe is believed to have undergone a brief but extraordinary phase known as cosmic inflation. During this period, space itself expanded at an exponential rate, faster than the speed of light. Tiny quantum fluctuations, smaller than atoms, were stretched across cosmic scales. These fluctuations became the seeds of all structure. Galaxies, clusters, the cosmic web. Everything we see today can be traced back to these initial irregularities. But inflation also implies something profound. If the universe expanded so rapidly in its earliest moments, then regions beyond our observable horizon may be vastly larger and fundamentally disconnected from us. Entire domains of space, entire cosmic regions, forever beyond reach. One of the most fascinating ideas in modern cosmology is the possibility that our universe is not the only one. This concept, known as the multiverse, emerges naturally from certain models of cosmic inflation. According to these models, inflation may not have occurred just once. Instead, it could be an ongoing process, creating bubble universes continuously, each with its own physical properties. Our universe could be just one bubble among countless others, each with different laws of physics, different constants, different histories. While this idea remains highly speculative, it offers a potential explanation for some of the mysteries we observe. Why do the fundamental constants of nature appear finely tuned for the existence of life? Why does the universe have the structure it does? In a multiverse, the answer could be simple. We exist in a universe where the conditions happen to allow it. And the discoveries of the James Webb Space Telescope, revealing unexpected complexity and early structure, add to the sense that reality may be far broader than we once believed. Is the universe a simulation? Another idea, controversial yet increasingly discussed, is the possibility that reality itself may not be fundamental. The simulation hypothesis suggests that the universe could be a constructed environment, governed by underlying rules similar to a computational system. While this concept often appears in philosophy and science fiction, some scientists have explored it from a theoretical perspective. If the universe operates according to mathematical laws, if reality is fundamentally informational, could it, in principle, be simulated? There is no direct evidence for this idea. But the deeper we explore the universe, the more we encounter patterns, structures, and behaviors that raise fundamental questions about the nature of reality itself. And as the James Webb Space Telescope continues to reveal unexpected phenomena, those questions only grow more profound. The journey of discovery is far from over. The James Webb Space Telescope represents just the beginning of a new era in astronomy. In the coming decades, even more powerful instruments will join the search. Next-generation space telescopes may be capable of directly imaging Earth-like planets around distant stars. Massive ground-based observatories will analyze the atmospheres of exoplanets, searching for signs of life. Advanced detectors will probe the nature of dark matter and dark energy with unprecedented precision. Each new instrument will expand our reach. Each discovery will refine our understanding. And each answer will lead to new questions. For thousands of years, humans have looked up at the night sky and wondered about their place in the universe. Were we at the center of everything? Or just a small part of something far greater? Science has answered that question. We are not at the center. We are not even close. We live on a small planet orbiting an ordinary star, located in the outer region of a typical galaxy, one among billions. And yet, there is something extraordinary about our existence. We are part of the universe, and at the same time we are able to understand it. Atoms formed in ancient stars now form our bodies. Processes that began billions of years ago have led, step by step, to conscious beings capable of asking questions about their origins. In this sense, the universe is not just something we observe. It is something we are part of. As the data from the James Webb Space Telescope continues to accumulate, one message is becoming increasingly clear. The universe may not be what we thought it was. Galaxies are forming earlier. Structures are emerging faster. Measurements are conflicting. And the models we relied on are being tested in ways we did not expect. This is why some scientists, including Adam Rees, have suggested that we may be looking at a universe that behaves differently than our theories predict. Not completely wrong, but different. A universe that is more dynamic, more complex, more surprising. In the end, the story of the universe is not a finished narrative. It is an unfolding journey. Every generation builds on the discoveries of the past. Every new instrument reveals a deeper layer of reality. And every answer opens the door to new mysteries. The James Webb Space Telescope has shown us that the cosmos is not only vast, but unpredictable, that even our best theories can be challenged, that even our most confident assumptions can be overturned, and that the universe still holds secrets beyond imagination. Perhaps the most important realization is this: we are not at the end of discovery. We are at the beginning, standing at the edge of a vast, unknown ocean, just beginning to explore what lies beyond the horizon. And somewhere, in the faint light of distant galaxies, in signals that have traveled across billions of years, the universe is still speaking, waiting for us to understand. When the James Webb Space Telescope began its first deep observations, astronomers expected surprises. But not like this. One of the most important early survey programs was known as CERS, the Cosmic Evolution Early Release Science Survey. Its goal was simple: look deep into the universe and identify some of the earliest galaxies ever formed. What it found challenged expectations almost immediately. Astronomers identified galaxies with redshift values greater than 10, meaning their light had been traveling for more than 13 billion years. These galaxies existed when the universe was less than 500 million years old. That alone was remarkable. But what truly shocked scientists was their size and brightness. These were not faint, barely detectable objects. They were luminous, massive, structured. Some appeared to contain billions of stars, comparable to galaxies that, according to standard models, should have taken billions of years to form. Another program, known as GLASS, Grism Lens Amplified Survey from Space, revealed similar results. Using gravitational lensing, where massive galaxy clusters bend and magnify distant light, astronomers were able to observe even fainter and more distant objects. And once again, the pattern repeated. Galaxies were appearing earlier than expected, and they were far more developed than theory allowed. To understand why this is such a problem, consider the timeline of cosmic evolution. After the Big Bang, the universe needed time to cool down, form atoms, collapse gas clouds, ignite stars, build galaxies. Each step takes time. Yet Webb is showing us galaxies that seem to have skipped ahead, as if the universe accelerated its own development. To truly understand these discoveries, we need to understand one key concept: redshift. When light travels through an expanding universe, its wavelength stretches. The farther it travels, the more it stretches. This shift toward longer wavelengths, toward the red end of the spectrum, is called redshift. Astronomers use redshift as a kind of cosmic timestamp. Higher redshift means greater distance, earlier time in the universe. For example, redshift 1 billions of years ago, redshift 6 very early universe, redshift 10 plus near the first galaxies. The James Webb Space Telescope has detected galaxies at redshifts beyond 10, and possibly even higher. This pushes observations closer to the very beginning of cosmic history than ever before. But here's the problem. At those redshifts, galaxies should be small, primitive, barely forming. Instead, they are large and bright, which suggests either our interpretation of redshift is incomplete, or galaxy formation happened much faster, or something more fundamental is wrong. And that's where the tension begins. To form a galaxy, the universe must perform a complex sequence of steps. First, matter must gather under gravity. Then gas clouds must collapse. Stars must ignite. Supernova explosions must enrich the environment with heavier elements. Structures must stabilize. This process is not instant. It is gradual, or at least, that's what we believed. But Webb's observations suggest that galaxy formation may have occurred at extreme speeds in the early universe. Star formation rates may have been dramatically higher. Gas densities may have been greater. Cooling processes may have been more efficient. In some scenarios, galaxies could have formed in intense bursts, producing enormous numbers of stars in very short periods of time. But even the most aggressive models struggle to explain the largest galaxies observed, which leads to an uncomfortable possibility. The early universe may have operated under conditions we don't yet fully understand. Light doesn't just show us where galaxies are, it tells us what they're made of. By analyzing the spectrum of light from distant galaxies, astronomers can identify the chemical elements present within them. This technique, known as spectroscopy, reveals a hidden story. The earliest stars in the universe were composed almost entirely of hydrogen and helium. Heavier elements like carbon, oxygen, and iron were created later through nuclear reactions inside stars and supernova explosions. So, in the early universe, galaxies should be chemically simple. But Webb is detecting galaxies with surprisingly complex chemical signatures. This suggests that multiple generations of stars may have already lived and died within these galaxies. Which again raises the same question. How did this happen so quickly? The standard model of cosmology, the lambda-CDM model, relies heavily on dark matter. Dark matter provides the gravitational scaffolding for galaxy formation. Without it, galaxies would not form as efficiently. But what if dark matter behaved differently in the early universe? Some theoretical models suggest that dark matter could have been more densely concentrated, more interactive, more influential in early structure formation. If dark matter clumped faster or more strongly, it could have accelerated galaxy formation. But this idea comes with challenges, because any change to dark matter behavior must still match observations of the modern universe. And so far, no model perfectly explains both. Before rewriting the laws of physics, scientists must consider another possibility. What if the observations themselves are misleading? Astronomy is an incredibly complex field. Distances are inferred. Masses are estimated. Brightness is interpreted. It is possible that some of the early galaxy measurements are overestimated. For example, brightness may be amplified by gravitational lensing. Star populations may be different than assumed. Dust may affect observations. However, even after accounting for these uncertainties, the overall pattern remains. The early universe still appears more evolved than expected, which means the mystery remains unsolved. Science does not progress in a straight line. It moves in cycles. Periods of stability are followed by moments of disruption, when new data forces a reevaluation of everything. We may be entering such a moment now. The discoveries of the James Webb Space Telescope are not small anomalies. They are consistent patterns, repeated observations, signals that something deeper may be happening. If confirmed, these findings could lead to new models of galaxy formation, new theories of dark matter, even modifications to gravity itself. Moments like this are rare, but when they happen, they reshape our understanding of reality. What if the universe is more efficient than we thought? One possibility is not that our theories are wrong, but that the universe is simply more efficient, more capable, more dynamic. Perhaps the early universe was a place of intense activity, where matter collapsed rapidly, stars formed explosively, and galaxies assembled at astonishing speeds. If this is true, then Webb is not breaking cosmology. It is revealing its true complexity, a universe that is not slow and gradual, but fast and powerful. There is something deeply human about this moment. For centuries, we have tried to understand the universe, to map it, to explain it, and now, just as we begin to feel confident, it surprises us again, reminding us that we are still learning, still exploring, still at the beginning. If there is one lesson from all of this, it is this: the universe is not simple. It does not follow easy rules. It does not behave in ways that are always predictable. It is vast, dynamic, complex beyond imagination. And every time we look deeper, we find something new. To understand why the discoveries of the James Webb Space Telescope are so important, we must first understand one of the most fundamental properties of the universe. It is expanding. This idea was first discovered in the early 20th century, when astronomers observed that distant galaxies were moving away from us. The farther away a galaxy was, the faster it appeared to recede. This observation led to a revolutionary conclusion. Space itself is stretching. A common way to visualize this is the balloon analogy. Imagine dots drawn on the surface of a balloon. As the balloon inflates, the dots move away from each other. Not because they are traveling across the surface, but because the surface itself is expanding. This is how the universe behaves. Galaxies are not simply moving through space. They are being carried apart as space expands between them. This expansion affects everything, from the large-scale structure of the cosmos to the light we observe from distant galaxies. And it plays a critical role in how we interpret Webb's discoveries. At the heart of cosmic expansion lies a single number, the Hubble constant. This value tells us how fast the universe is expanding. In simple terms, it describes the relationship between distance and velocity. The farther a galaxy is, the faster it moves. Either our measurements are flawed, or our understanding of the universe is incomplete. The second possibility is far more interesting, because it suggests that something fundamental is missing from our models. And now, with data from the James Webb Space Telescope, this tension is becoming harder to ignore. Measuring distances in space is one of the greatest challenges in astronomy. We cannot stretch a measuring tape across the universe. Instead, scientists rely on a method known as the cosmic distance ladder. This system uses a series of overlapping techniques. Nearby stars are measured using parallax. Slightly farther stars use Cepheid variables, stars that pulse in brightness. Even farther distances rely on supernova explosions. Each step builds on the previous one. But if even one step is slightly off, the entire ladder becomes unstable. This is why the Hubble tension is so difficult to resolve, and why Webb's precise measurements are so important. In 1998, astronomers made one of the most shocking discoveries in modern science. The universe is not just expanding, it is accelerating. Something is pushing galaxies apart at an increasing rate. This mysterious force is known as dark energy. It makes up about 68% of the universe. And yet, we don't know what it is. Some theories suggest it is a property of space itself. Others propose entirely new forms of energy. And some scientists believe it may indicate that our understanding of gravity is incomplete. If Webb's observations are affecting measurements of cosmic expansion, then they may also be revealing new clues about dark energy. Gravity is the architect of the universe, pulls matter together, forms stars, builds galaxies, shapes the cosmic web. Our current understanding of gravity comes from Einstein's theory of general relativity, a framework that has been tested and confirmed many times. Either our measurements are flawed, or our understanding of the universe is incomplete. The second possibility is far more interesting, because it suggests that something fundamental is missing from our models. And now, with data from the James Webb Space Telescope, this tension is becoming harder to ignore. Measuring distances in space is one of the greatest challenges in astronomy. We cannot stretch a measuring tape across the universe. Instead, scientists rely on a method known as the cosmic distance ladder. This system uses a series of overlapping techniques. Nearby stars are measured using parallax. Slightly farther stars use Cepheid variables, stars that pulse in brightness. Even farther distances rely on supernova explosions. Each step builds on the previous one. But if even one step is slightly off, the entire ladder becomes unstable. This is why the Hubble tension is so difficult to resolve, and why Webb's precise measurements are so important. In 1998, astronomers made one of the most shocking discoveries in modern science. The universe is not just expanding, it is accelerating. Something is pushing galaxies apart at an increasing rate. This mysterious force is known as dark energy. It makes up about 68% of the universe. And yet, we don't know what it is. Some theories suggest it is a property of space itself. Others propose entirely new forms of energy. And some scientists believe it may indicate that our understanding of gravity is incomplete. If Webb's observations are affecting measurements of cosmic expansion, then they may also be revealing new clues about dark energy. Gravity is the architect of the universe, pulls matter together, forms stars, builds galaxies, shapes the cosmic web. Our current understanding of gravity comes from Einstein's theory of general relativity, a framework that has been tested and confirmed many times. But it may not be complete. On cosmic scales, gravity behaves in ways that require the existence of dark matter and dark energy to explain observations. Some scientists are exploring the possibility that gravity itself may need to be modified. If this is true, then Webb's discoveries could be pointing toward a deeper theory of the universe. Could time behave differently in the early universe? Time is something we take for granted. It flows steadily, predictably. At least that's how it feels. But in physics, time is not absolute. It can stretch, slow down, speed up. In extreme conditions, such as near massive objects or during the early moments of the universe, time may behave differently. Some speculative ideas suggest that processes in the early universe may have occurred under different temporal conditions. If true, this could affect how we interpret cosmic timelines, making events appear faster or slower than they actually were. While this idea remains theoretical, it highlights an important point. Our understanding of time itself may be incomplete. Even with the incredible power of the James Webb Space Telescope, there are limits to what we can observe. Light can only travel so far. Signals can only reach us from certain regions. Beyond that, the universe remains hidden. This means that all of our models are based on incomplete data. We are trying to understand an infinite system using a finite window. And that makes uncertainty unavoidable. There is a boundary in science, a place where knowledge ends and uncertainty begins. Right now, we are standing at that boundary. The discoveries of the James Webb Space Telescope are pushing us beyond what we thought we knew, into territory where answers are not yet clear, where theories are still forming, where the universe feels unfamiliar. Why this changes everything. If these discoveries hold true, then we may need to rethink how galaxies form, how fast the universe evolved, what dark matter really is, what dark energy really does. This is not just a small update. It is a shift in perspective, a reminder that science is always evolving, always questioning, always searching. When the first deep-field images from the James Webb Space Telescope were released, astronomers expected something simple, a clearer view of early galaxies. But what they saw instead changed the conversation immediately. Tiny, bright, structured galaxies appeared in regions of space that should have been almost empty in the early universe. These galaxies were not just present, they were surprisingly developed. Some had shapes resembling modern spiral or elliptical structures. This raised a serious question. How did they form so quickly after the Big Bang? One of the most important datasets came from the SEWER survey, Cosmic Evolution Early Release Science. This program was designed specifically to study early galaxy formation. What it found surprised researchers. Several galaxies appeared at extremely high redshifts, meaning they existed very early in cosmic history. Some of these galaxies were so massive that they should not have had enough time to form under standard models of cosmic evolution. This did not break physics, but it pushed the limits of what current models predicted. Some of the earliest JWST observations revealed galaxies that were too massive, too bright, too mature for their age. In simple terms, they looked too evolved for the early universe. Under the standard lambda-CDM model, galaxies should start small and gradually grow through mergers and gas accumulation. But JWST showed examples that seemed to have grown too quickly. This raised a major scientific tension. Either galaxy formation happened faster than expected, or something fundamental is missing from our understanding. To understand why these galaxies are so surprising, we need to understand redshift. When light travels through expanding space, its wavelength stretches. This shifts it toward the red and infrared part of the spectrum. The more distant a galaxy is, the higher its redshift value. JWST is designed to detect this infrared light with extreme sensitivity. That's why it can see further back in time than any previous telescope. But when astronomers calculated the redshifts of some early galaxies, the results implied they formed much earlier than expected. This is where the tension begins. Another major discovery came from the detection of extremely bright quasars in the early universe. These quasars are powered by supermassive black holes. But here's the problem. These black holes appear too large for their age. Standard models suggest black holes grow slowly over time. But JWST observed black holes that seem to have grown extremely rapidly after the early universe formed. This creates another puzzle. How did they grow so fast? Possible explanations include faster than expected accretion, early massive seed black holes, or unknown physics of black hole formation. When data starts to challenge models, science does not collapse when new data appears. Instead, it adapts. But sometimes, data pushes models to their limits. That is what is happening now. Researchers are comparing observed galaxy formation timelines, predicted simulations from the Lambda CDM model, and the mismatch is becoming harder to ignore. This does not mean the model is wrong, but it may mean it is incomplete. To understand the universe, scientists run massive simulations. These simulations recreate gravity, dark matter behavior, gas formation, galaxy clustering. They help predict how the universe should look at different stages. But JWST data is now being compared against these simulations, and some early results don't align perfectly. This raises a serious scientific question. Are we missing key physics in our simulations? One of the leading explanations is surprisingly simple. Maybe structures in the early universe formed faster than we thought. This could mean gravity acted more efficiently, gas collapsed quicker, or dark matter clumped differently. But each explanation introduces new questions. Because changing one variable affects the entire cosmic timeline. It is important to understand something clearly. The universe is not breaking. Our understanding of it is evolving. Every major telescope in history has done this. Hubble Space Telescope expanded our view of galaxies. James Webb Space Telescope is now expanding our timeline of cosmic history. Each step brings both clarity and confusion. That is how science progresses. The deeper JWST looks, the more complex the early universe appears. Instead of a simple, slow buildup of galaxies, we see rapid structure formation, massive early objects, unexpected brightness, fast black hole growth. Each discovery adds another layer to the mystery. We may be witnessing the early stages of a major scientific shift. Not a collapse of physics, but a refinement, a deeper version of cosmology that includes new galaxy formation physics, better understanding of dark matter, more accurate expansion history. Why scientists are calling it a different universe? When researchers analyze the data from the James Webb Space Telescope, one phrase keeps appearing in discussions. It feels like a different universe. This does not mean a literal new universe exists. It means the early universe looks unexpectedly different from what standard models predicted. Galaxies appear too quickly. Black holes appear too massive. Structures appear too mature. And all of this is happening far earlier than expected in cosmic history. This is why scientists like Adam Rees and others have raised concern, not as alarm but as scientific curiosity. Because the data is consistent, yet surprising. At this point, scientists generally consider three major possibilities. 1. Measurement errors, least exciting but possible. There may still be subtle calibration issues in distance measurement, redshift interpretation, luminosity calculations. Even small errors can scale dramatically in cosmology. 2. Faster early universe evolution. Another possibility is that The early universe evolved faster than our models predict. This could mean gravity worked more efficiently, gas cooled faster, dark matter clumped earlier. This would reshape timelines but not break physics. 3. New physics, most revolutionary possibility. The most exciting possibility is also the most controversial. Our current model of the universe may be incomplete. This could involve new properties of dark matter, unknown interactions in early cosmic inflation, modifications to gravity on large scales. This does not replace modern physics, it expands it. Why this doesn't break the Big Bang theory? Many people misunderstand these discoveries. The Big Bang is not being disproven. Instead, what is being refined is how galaxies formed after the Big Bang, how fast structures appeared, how matter evolved in early stages. The Big Bang remains the foundation, but the details around it are becoming more complex. Science is often described as logical and mathematical, but in reality, discovery is deeply emotional. When researchers first saw unexpected JWST data, reactions included shock, confusion, excitement, curiosity, because every unexpected result is a doorway into something unknown. What different universe really means. The phrase does not mean a parallel universe, a multiverse confirmation, or alternate reality. Instead, it means the early universe behaves in ways we did not expect. Our models may be missing key elements. Cosmic evolution may be more complex than assumed. It is a scientific statement, not science fiction. One of the most important lessons from this discovery is perspective. Humans once believed Earth was the center of everything. The galaxy was the entire universe. The universe was static. Each time we were wrong, but in a way that expanded understanding. Now, JWST is doing the same again. Are we missing something fundamental? Some scientists believe we are approaching a new turning point. Not because old theories are useless, but because they may be incomplete. Possible missing pieces include better understanding of dark matter, more accurate early universe physics, improved models of galaxy formation. The universe is not contradicting itself. It is revealing complexity we had not yet accounted for. The universe itself has not changed. What has changed is our ability to observe it. The James Webb Space Telescope is simply revealing earlier galaxies,
Faste formation.
deeper cosmic history, and every new image adds another layer to the mystery. We are now in a rare moment in science, a moment where data is ahead of theory, observations are outpacing explanations, and questions are multiplying faster than answers. This is not a crisis. It is progress. Every time humanity believes it understands the universe, something changes. At first, the cosmos seemed simple. Stars fixed in the sky, a static universe, a predictable structure. Then came expansion. Then came dark matter. Then came dark energy. And now, with the James Webb Space Telescope, we are seeing something even more complex. A universe that does not fit neatly into our expectations. Not broken, not random, but deeply layered in ways we are only beginning to understand. Across all observations, a pattern emerges. Early galaxies appear too quickly. Black holes grow too fast. Structures form earlier than expected. Expansion measurements disagree slightly. Individually, each result can be explained. But together, they suggest something deeper. We may be missing part of the cosmic puzzle. When Nobel Prize-winning scientists describe the universe as different, they do not mean it has changed. They mean our previous picture of it was incomplete. The universe is still governed by the same laws. But the early conditions appear more extreme, more efficient, and more complex than we assumed. It is like discovering that a familiar book has additional hidden chapters. The story was always there. We just couldn't see it. What the James Webb era represents. The James Webb Space Telescope is not just another telescope. It represents a shift in human capability. For the first time, we are seeing galaxies as they formed. We are observing the earliest structures. We are testing the limits of cosmological theory. It is a machine built not just to observe space, but to rewrite history. Science is not about having answers. It is about refining questions. And right now, the questions are becoming sharper. How did galaxies form so early? Why do black holes appear so massive so soon? Is dark matter behaving differently in the early universe? Is our model of expansion fully correct? Each question leads to another. Each answer opens a deeper mystery. One of the most important realizations in modern cosmology is this: the universe is not changing its behavior. We are improving our ability to observe it. The more we see, the more complex it appears. Not because reality is unstable, but because reality is richer than our models. Humanity is living in a unique moment. For the first time in history, we can observe the early universe directly. We can test cosmological models in real time. We can compare prediction with reality at cosmic scale. This is not just discovery. It is participation in understanding creation itself. At the edge of what we know, one truth becomes clear. The universe is not finished revealing itself. Every galaxy observed by JWST is a message from the past. Every unexpected structure is a clue. Every anomaly is an invitation to think deeper. And perhaps the greatest discovery is not what we find out there, but what we realize about our own understanding. The universe is vast, older than imagination, stranger than prediction, and still unfolding in front of us. The James Webb Space Telescope has not ended the story of cosmology. It has only opened the next chapter. And in that chapter, one idea stands above all. We are still learning what reality truly is. We began with a warning. It's a different universe. And we end with understanding. It was never a different universe. It was always the same universe. We were simply seeing it clearly for the first time. Subscribe for more space documentaries, because the universe is just getting started.